For the Certified Kubernetes Admin, implement storage classes and dynamic volume provisioning in the storage section in 2,000 words. Here's a 2,000-word text-to-speech friendly guide to help you master the implement storage classes and dynamic volume provisioning topic for the Certified Kubernetes Administrator CKA exam. It's written in an educational, exam-aligned, and example-driven style, without code blocks requiring visual inspection. Implementing storage classes and dynamic volume provisioning. 1. Overview of storage in Kubernetes. Kubernetes applications often require storage that outlives pod lifecycles. Pods are ephemeral, meaning when they are deleted or rescheduled to another node, their file system data is lost unless stored externally. Kubernetes provides an abstraction over storage using persistent volumes, PVs, and persistent volume claims, PVCs, and an automated layer using storage classes and dynamic provisioning. In a nutshell, persistent volume, PV, represents a piece of storage in the cluster. It's a resource provisioned either statically by an administrator or dynamically by a provisioner. Persistent volume claim, PVC, a request for storage by a user or workload. Storage class defines a type of storage and the rules or provisioner for dynamically creating PVs. Understanding the relationship between these three is critical for both real-world cluster operations and the CKA exam. 2. Persistent volumes and persistent volume claims. Recap. Before dynamic provisioning can make sense, you need to understand static provisioning. Static provisioning. An administrator manually creates PVs ahead of time. Each PV defines its capacity, access modes, and the underlying storage, such as NFS, EBS, Ceph, or local disk. When a user creates a PVC, Kubernetes finds a PV that matches the request. This approach has drawbacks. 1. Requires the cluster admin to pre-create PVs. 2. Can lead to wasted capacity if PVs remain unclaimed. 3. Doesn't scale well in dynamic environments. Dynamic provisioning was designed to solve this. Instead of pre-creating volumes, Kubernetes can automatically create them when a PVC is submitted, using a storage class that defines the type of storage and how to provision it. 3. The role of storage classes. A storage class object defines how Kubernetes should dynamically provision a PV when a PVC requests it. It has 3 major parts. 1. Provisioner, the plugin or driver responsible for creating volumes. 2. Parameters, configuration options passed to the backend. 3. Reclaim policy and binding mode, rules for how volumes are recycled and bound. Think of a storage class as a blueprint for how to create storage dynamically. Common provisioners. Each environment provides a different storage backend. The provisioner field in a storage class determines which controller handles the creation of volumes. Common examples include Kubernetes.io AWS EBS for AWS EBS volumes, deprecated in favor of CSI. Kubernetes.io GCE PD for Google Cloud Persistent Disks. Kubernetes.io Azure Disk for Azure. Kubernetes.io NFS for NFS, typically static. CSI-based drivers such as ebs.csi.aws.com, pd.csi.storage.gke.io, csi.trident.netapp.io, rockceph.rbd.csi.ceph.com, disk.csi.azure.com. In modern clusters, CSI drivers, Container Storage Interface, are the preferred method. They allow vendors to plug into Kubernetes using a consistent interface rather than the older in-tree drivers. 5. Key fields in a storage class. Let's conceptually break down its components. Provisioner specifies the driver that performs volume creation. Example, ebs.csi.aws.com. Parameters. These are driver-specific options such as volume type, GP3 IO1 for AWS EBS, file system, ext4 XFS, IOPS or throughput, reclaim policy, Defines what happens to the PV when its bound PVC is deleted. Delete. The volume is automatically deleted from the backend. Retain. The volume remains. Manual cleanup is required. Recycle. Deprecated, used to wipe data and reuse. Rarely seen now. Most dynamic storage uses delete for automatic cleanup. Volume binding mode. Determines when and where the volume is provisioned. Immediate default. Volume is provisioned as soon as the PVC is created. Wait for first consumer. Volume creation is delayed until a pod using the PVC is scheduled. This helps ensure the volume is provisioned in the same zone as the pod, preventing zone mismatch errors, especially important on AWS or GCP. Allowed topologies. Defines where volumes may be created, typically based on zone labels. 6. How dynamic provisioning works. Dynamic provisioning is a sequence of coordinated actions involving multiple Kubernetes components. Here's the step-by-step flow. 1. User submits a persistent volume claim. The PVC specifies the desired size, access mode, and optionally a storage class name. 2. Kubernetes finds the corresponding storage class. It looks up the storage class name in the cluster to determine the provisioner and parameters. 3. Provisioner plugin creates a volume. The CSI controller or in-tree driver talks to the underlying storage API, like AWS, GCE, Ceph, to create a new disk or share. 4. A persistent volume is created. Kubernetes automatically creates a PV object representing this new volume and binds it to the PVC. 5. Pod uses the PVC. Once bound, a pod referencing that PVC can mount it as a file system volume. 6. When the PVC is deleted. Depending on the reclaim policy, delete or retain, the actual backend volume may be deleted or kept for manual handling. This process allows developers to request storage as easily as they request CPU and memory, removing the need for admin intervention. 7. Access modes. Access modes define how a volume can be mounted by pods. They are crucial in selecting compatible PVs or provisioning the right type of volume. The main access modes are read-write once, RWO. Volume can be mounted as read-write by a single pod. Read-only many, ROX. Volume can be mounted as read-only by many nodes. Read-write many, RWX. Volume can be mounted as read-write by many nodes simultaneously. Read-write once pod, RWOP. Volume can be mounted by only one pod, even across nodes, CSI specific. For example, AWS EBS supports only RWO, while NFS or CFS or CEFFS supports RWX. Choosing the wrong access mode can cause PVCs to remain unbound. 8. Binding and provisioning scenarios. The interplay between PV, PVC, and storage class can be subtle. Understanding it helps avoid exam traps. Scenario 1. PVC without a storage class name. If a PVC does not specify a storage class name, and no default storage class exists, no dynamic provisioning occurs. The PVC waits for a manually created PV. Scenario 2. PVC with storage class name. If a valid storage class name is provided, Kubernetes dynamically provisions the volume using that class. Scenario 3. PVC with storage class name set to empty string. This explicitly disables dynamic provisioning, even if a storage class exists. Scenario 4. Default storage class. You can mark a storage class as default by labeling it storageclass.kubernetes.io is default class, true. When users create PVCs without specifying a storage class name, the default one is used automatically. 9. CSI drivers and external provisioners. Dynamic provisioning relies on external provisioners, controllers that implement the logic for creating and deleting storage. CSI drivers are deployed as pods in the cluster. Controller plugin runs as the deployment, handles creation, deletion of volumes. Node plugin runs as a daemon set, handles mounting, unmounting on nodes. The storage class provisioner name matches the driver's identifier, such as ebs.csi.aws.com. These drivers communicate with the cloud or storage system APIs and expose standard gRPC endpoints defined by the Container Storage Interface (CSI) specification. 10. Troubleshooting binding issues. For the exam, you might encounter a PVC stuck in pending state. Here's a mental checklist to diagnose the cause. 1. Check the PVC events. Run kubectl describe PVC name. Look for messages like waiting for a volume to be created, no storage class found, no matching PV available, driver failed to create volume. 2. Verify storage class exists and matches. Ensure the PVC storage class name corresponds to a valid storage class. 3. Check the provisioner pods. For CSI, make sure the controller pods are running and not in crash loop backoff. 4. Confirm volume binding mode. If wait for first consumer, the PV won't be created until a pod requests the PVC. 5. Validate access modes. Ensure the PVC's requested access modes is supported by the backend. 6. Check node affinity zones. If you're using multi-zone storage like AWS EBS, ensure pods and volumes align to the same zone. For the CKA exam, if you get a scenario like PVC stuck in pending, these 6 points are your map to a correct, quick resolution. 11. The life cycle of a dynamically provisioned volume. Understanding the full life cycle helps you reason about cleanup and quota. Step 1. PVC creation. User defines a claim with the size and access mode. Kubernetes defines the storage class. 2. PV creation. The provisioner communicates with the backend, for example, AWS API, and creates a new volume. Step 3. PV/PVC binding. Kubernetes creates a PV object, marks it with claim ref, and binds it to the PVC. Step 4. Pod mount. A pod with a volume mount referencing the PVC causes the kubelet to attach and mount the volume via the node plugin. Step 5. Pod determination. When the pod ends, kubelet unmounts the volume. Step 6. PVC deletion. If the PVC is deleted, Kubernetes checks the reclaim policy. If delete, the backend volume is destroyed. If retain, the PV object remains for manual reclamation. Step 7. PV reuse. If retained, the admin can clean and manually reassign the PV to a new PVC by removing the claim ref. 12. Static versus dynamic provisioning, a comparison. Feature. Who creates the PV? Static provisioning, the administrator. Dynamic provisioning, Kubernetes provisioner. Feature. When is PV created? Static provisioning, before PVC. Dynamic provisioning, after PVC. Feature. Flexibility, static provisioning, low. Dynamic provisioning, high. Feature. Scalability, static provisioning, poor. Dynamic provisioning, excellent. Feature. Admin overhead, static provisioning, high. Dynamic provisioning, minimal. Feature. Common usage, static provisioning, legacy or special volumes. Dynamic provisioning, default in modern clusters. In short, static provisioning is manual and error-prone. Dynamic provisioning is automated, self-service, and standard for production clusters. 13. Example use cases and cloud implementations. AWS EBS example. Provisioner, ebs.csi.aws.com. Parameters, volume type, IOPS, file system. Reclaim policy, delete. Access mode, read-write once. Limitation, EBS volumes can be attached to one node at a time. GCP persistent disk example. Provisioner, pd.csi.storage.gke.io. Supports RWO and RWX, depending on disk type. Zonal binding enforced with wait for first commuter. Zonal binding enforced with wait for first consumer. Azure Disk. Provisioner, disk.csi.azure.com. Supports SSD and HDD tiers, typically used for RWO workloads. CephFS or NFS. Provisioner, CSI CephFS or NFS subdir external provisioner. Supports read-write-many. Common for shared storage in clusters. Knowing which storage backends support RWX versus RWO is a common exam trick. 14. Storage class defaults and deletion behavior. In clusters with multiple storage classes, one can be the default. You can identify or change the default with these steps conceptually. Check defaults. kubectl get storage class. Mark 1 as default. Annotate with storage class.kubernetes.io is default class true. Remove default behavior. Annotate with false or delete the annotation. When PVCs are deleted, if reclaim policy equals delete, Kubernetes automatically calls the driver to delete the backend volume. If reclaim policy equals retain, the admin must manually remove it later. You might see exam questions asking what happens when PVCs are deleted under different reclaim policies. Make sure you remember those differences. 15. Dynamic provisioning on local volumes. While cloud storage is common, you can also use local storage provisioners. The local path provisioner from Rancher or similar controllers dynamically create host path-based PVCs, host path-based PVs on local disks. They're ideal for single node clusters like Minikube or Kind, often used in the exam environment. In such cases, provisioner, rancher.io local path, storage class, local path. Volumes are directories on the node's file system. Reclaim policy, usually delete. If you use Minikube or Kind to practice, this is the easiest way to experiment with dynamic provisioning locally. 16. Monitoring and inspecting storage behavior. You can verify storage behavior using the following workflow. Conceptually, no commands were required for this understanding. 1. List storage classes to identify which one is default. 2. Describe PVCs to view their events and bound PVs. 3. Inspect PVs to confirm capacity, access mode, and reclaim policy. 4. Check CSI controller logs if provisioning fails. Exam tasks might require you to verify that a PVC has been dynamically provisioned and bound. Ensure you can reason about the resource relationships quickly. 17. Quotas and limits. Administrators can use resource quotas and limit ranges to control storage consumption per namespace. Example concepts: requests.storage, the total requested size of PVCs. Persistent volume claims, the number of PVCs allowed. Dynamic provisioning respects these quotas. If a namespace exceeds the limit, PVC creation fails. 18. Volume expansion. Most CSI drivers support volume resizing. If a PVC requests a larger size and the storage class has allow volume expansion true, Kubernetes can dynamically expand the volume. Key points. The PVC must be bound to a driver that supports expansion. The storage class must explicitly enable it. The pod may need to restart for the file system to resize. This feature often appears as a follow-up question to dynamic provisioning topics. 19. Security and isolation considerations. Dynamic provisioning simplifies developer workflows, but admins must enforce good practices. 1. Namespace isolation. PVCs are namespace scoped, while PVs are cluster scoped. Proper RBAC and quotas prevent tenants from exhausting cluster storage. 2. Reclaim policy awareness. Ensure sensitive data isn't left behind when using retain. 3. Encryption. Many CSI drivers support encryption at rest. Parameters can enable this. 4. Snapshots and clones. Some drivers support volume snapshot class for backups and cloning. This extends the concept of dynamic provisioning to snapshot creation. 20. Common exam tasks. Expect tasks such as 1. Create a storage class. You'll be given parameters like provisioner and reclaim policy. 2. Create a PVC that uses it. Ensure it binds successfully and verify the resulting PV. 3. Deploy a pod that uses the PVC. Confirm the volume is mounted and writable. 4. Delete the PVC and observe cleanup. Verify whether the PV and backend volume are deleted or retained. 5. Troubleshoot a stuck PVC. You might need to modify storage class name, access modes, or binding mode. Being fast at reading YAML and understanding these relationships saves time during the exam. 21. Practical analogy. Think of storage class and dynamic provisioning like hotel bookings. Static provisioning. The hotel manager preassigns specific rooms before guests arrive. Guests, PVCs, must find a matching room, PV. This wastes capacity if guests never arrive. Dynamic provisioning. When a guest checks in, PVC created, the system automatically assigns and prepares a room, PV created, that fits their needs, size, view, amenities. When the guest leaves, PVC deleted, the room can be cleaned, reclaimed automatically. This analogy helps remember that storage class automates room creation at check-in time. 22. Tips for the CKA exam. 1. Know how to list and describe storage classes, PVs, and PVCs quickly. 2. Remember the role of storage class name. Omitted, default used. Empty string, disable dynamic provisioning. 3. Understand reclaim policies and binding modes conceptually. 4. Don't get stuck debugging zone mismatches. Check wait for first consumer. 5. Be comfortable with local path provisioners for lab environments. 6. Review the differences between static and dynamic provisioning thoroughly. During the CKA exam, you might not have internet access to refer to documentation. Memorizing these patterns helps you reconstruct YAMLs from memory. Summary. Dynamic volume provisioning transforms Kubernetes storage from a static, admin-driven model into an automated, on-demand system. The key components are storage class, blueprint defining how to create storage dynamically. Provisioner, driver implementing the logic, usually CSI. Persistent volume claim, user's request for storage. Persistent volume, the actual storage resource created dynamically. Together, they create a seamless experience where workloads can request persistent storage without manual steps. Administrators define the available storage types, developers consume them declaratively, and Kubernetes orchestrates the rest: provision, bind, mount, cleanup, and harmony. Don't worry about text-to-speech friendly. Use code examples and do this again in 2,000 words. Excellent. Here's the 2,000 word deep dive with YAML, examples and CLI steps on the CKA exam. Implement storage classes and dynamic volume provisioning. It's written exactly in the technical style expected of an experienced admin studying for the exam. Implement storage classes and dynamic volume provisioning. 1. Why storage matters in Kubernetes. Pods are ephemeral. When they die or move, their container file systems disappear. But many workloads, databases, message queues, web apps need persistent storage. Kubernetes provides persistent storage through persistent volumes, PVs, and persistent volume claims, PVCs, with automation via storage classes for dynamic provisioning. The goal of this section of the CKA is to understand how to define storage types via storage classes, enable automatic provisioning via CSI drivers, manage lifecycle and reclaim policies, troubleshoot binding issues between PVs and PVCs. 2. Static versus dynamic provisioning. Before storage classes, storage was provisioned statically. Kind, persistent volume. Spec, capacity, storage, 5 gigabytes. Access modes, read-write once. Persistent volume reclaim policy, retain. Host path, mount, data. Then a user would create a PVC. Kind, persistent volume claim. Spec, access modes, read-write once. Resources, requests, storage, 5 gigabytes. Kubernetes tries to match PVs with PVCs with PVs that satisfy the request. Static provisioning works but has clear downsides. Cluster admins must manually create PVs. Unused PVs waste resources. Not scalable for multi-tenant or cloud environments. Dynamic provisioning solves this. Admins define a storage class, and when a PVC requests storage, Kubernetes, via the provisioner, automatically creates the PV. 3. Anatomy of a storage class. A storage class defines how storage should be dynamically created, what provisioner to use, and what parameters to pass. Example, AWS EBS. Kind, storage class. Name, EBS GP3. Provisioner, ebs.csi.aws.com. Parameters, type GP3. FS type, ext4. Reclaim policy, delete. Volume binding mode, wait for first consumer. Allow volume expansion, true. Key fields. Provisioner. The driver that creates storage, CSI or in-tree. Parameters. Backend specific options like volume type or file system. Reclaim policy. What happens to PV after PVC deletion? Delete, retain, or rarely recycle. Volume binding mode. When and where to create the volume. Immediate or wait for first consumer. Allow volume expansion. Whether PVCs can later request more space. 4. Default storage class. If a PVC doesn't specify a storage class name, Kubernetes uses the default storage class. To mark one as default, kubectl annotate storage class, EBS GP3, storage class.kubernetes.io is default class, true. To remove default status, kubectl annotate storage class, EBS GP3, storage class.kubernetes.io is default class minus. Check which one is default. Kubectl get storage class. You'll see something like name, provisioner, reclaim policy, volume binding mode, age. EBS GP3, ebs.csi.aws.com. Delete. Wait for first consumer. Five, volume binding mode, explained. Immediate. The volume is provisioned as soon as the PVC is created. Useful for storage without topology constraints, e.g. NFS. Wait for first consumer. The volume is created only when a pod that uses the PVC is scheduled. Useful for zonal cloud storage, AWS, GCP, Azure, to avoid zone mismatches. Volume binding mode, wait for first consumer. Without this, a PVC might be created in zone US East 1A, even if the pod is scheduled in US East 1B, leading to mount failures. 6. Creating a PVC that triggers dynamic provisioning. Now that we have a storage class, a developer can simply create a PVC. Kind, persistent volume claim. Spec, access modes, read-write once. Resources, requests, storage, 10 gigabytes. Storage class name, EBS GP3. Once applied, kubectl apply -f pvc.yaml. Kubectl get PVC. My PVC, status bound. Volume, PVC, a GUID. Capacity, 10 gigabytes. Access modes, RWO. Storage class, EBS GP3. Age, 5 seconds. Kubernetes automatically 1. Calls the provisioner, ebs.csi.aws.com. 2. Creates an AWS EBS volume. 3. Creates a corresponding PV and binds it to the PVC. 7. Verifying the provisioned PV. Kubectl get PV. Kubectl describe PV, PVC, the hash. You'll see details such as capacity, storage class, reclaim policy, bound PVC reference, CSI driver information. 8. Using the PVC in a pod. A pod can mount this PVC just like a directory. Kind pod. Spec. Containers, a volume mount. Name storage, mount path, /data. Volumes, name storage. Persistent volume claim, claim name, my PVC. Once created, verify the mount inside the pod. Kubectl exec-it app pod -df-h/data. You should see the dynamically provisioned volume mounted at /data. 9. Cleanup and reclaim policy. When a PVC is deleted, Kubernetes checks the storage class's reclaim policy. Delete. The PV and backend volume are deleted. Retain. The PV object remains. Data is preserved until manually deleted. You can view the reclaim policy on PVs. kubectl get PV-O custom columns equals name.metadata.name, status.status.phase, reclaim.spec.persistent volume reclaim policy. You can edit a PV and manually reclaim it. kubectl patch PV name-p spec persistent volume reclaim policy delete. 10. Provisioners. CSI versus in-tree. In early Kubernetes versions, each cloud had an in-tree provisioner. For example, Kubernetes.io AWS EBS, Kubernetes.io GCE PD, Kubernetes.io Azure Disk. Now, Kubernetes uses CSI, Container Storage Interface, drivers, deployed as pods. CSI driver components, controller plugin, deployment, handles volume create, delete operations, node plugin, daemon set, mounts, unmounts, volumes on pods, on nodes. You can list installed CSI drivers. kubectl get CSI drivers. Example output, name, ebs.csi.aws.com. Attach required, true. Pod info on mount, false. Age, 3 days. 11. Local storage example for practice environments. If you're not on a cloud cluster, use the local path provisioner included in Minikube and Kind. Kind, storage class. Metadata, name, local path. Provisioner, rancher.io, local path. Reclaim policy, delete. Volume binding mode, wait for first consumer. PVC, kind, persistent volume claim. Spec, access modes, read write once. Resources, requests, storage, 2 GB. Storage class name, local path. Pod, kind pod. Spec, containers, volume mounts, name, vol, mount path / data. Volumes, name, vol, persistent volume claim, claim name, PVC local. This creates a directory, e.g. opt local path provisioner, on the node's disk. Access modes and compatibility. Access mode, read-write once, RWO. Mounted read-write by a single node. Typical backends, AWS EBS, Azure Disk, GCE PD. Access mode, read-only many, ROX. Read-only by multiple nodes. Typical backends, NFS, CephFS. Access mode, read-write many, RWX. Read-write by multiple nodes. Typical backends, NFS, GlusterFS, CephFS. Access mode, read-write once pod, RWOP. Exclusive to a single pod, CSI only. Typical backends, some CSI drivers. If a PVC requests RWX, but the driver supports only RWO, the PVC will remain pending. To check why, run kubectl describe PVC name. Look for events such as warning, provisioning failed, no compatible volume found. 13. Troubleshooting PVCs stuck in pending. Common causes. A. No storage class. PVC has a storage class name referencing a non-existent class. Warning, provisioning failed, storage class, wrong name, not found. Fix, correct or remove the field. B. Storage class missing. PVC omitted storage class name and there's no default. C. Unsupported access mode. Driver doesn't support requested mode, e.g. RWX on EBS. D. Topology conflict. When using zonal disks, the volume can attach to a pod in a different zone. Use wait for first consumer. E. Provisioner pod crash. Check. kubectl get pods -n kube system pipe to grep CSI. kubectl logs -n kube system CSI controller pod. 14. Expanding volumes dynamically. Most CSI drivers allow volume expansion if the storage class enables it. Allow volume expansion, true. To expand, kind, persistent volume claim. Spec, resources, requests, storage, 20 gigs. Once applied, check status. kubectl get PVC, my PVC. Eventually, you'll see file system resize pending, bound. Inside the pod, the file system will be resized automatically on next mount for CSI drivers that support online expansion. 15. Reclaim policy scenarios. Delete. Backend volume deleted automatically when PVC is deleted. Default for most dynamic storage classes. Retain. Admin manually reclaims or reuses PVs. Example workflow. kubectl delete PVC, my PVC. kubectl get PV. PV remains in released state. To reuse. kubectl patch PV, PV name -p, spec, claim ref, null. kubectl patch PV, PV name -p, spec, persistent volume reclaim policy, delete. Then a new PVC with matching specs can bind to it. 16. Combining multiple storage classes. You can define multiple storage classes for different performance tiers. Example, fast SSD versus cheap HDD. Kind, storage class. Metadata name, fast SSD. Provisioner, ebs.csi.aws.com. Parameters, type IO2. Reclaim policy, delete. Kind, storage class. Metadata name, cheap HDD. Provisioner, ebs.csi.aws.com. Parameters, type ST1. Reclaim policy, delete. Developers choose by specifying storage class name in their PVCs. Example, storage class name, fast SSD. 17. Checking events and relationships. To observe how the system links objects, kubectl get sc, PVC, PV. kubectl describe PVC, my PVC. kubectl describe PV, PV name. Look for volume binding mode, claim ref, reclaim policy, storage class matches. Exam tasks often require verifying those relationships. 18. Dynamic provisioning architecture. User PVC, Kubernetes API server. External provisioner, part of CSI controller. Talks to backend storage API, AWS, GCP, NFS. Creates PV and backend volume. Scheduler binds PVC to pod and node. Node plugin mounts volume into container. When you delete the PVC, the provisioner detects it and deletes both PV and backend volume, if delete policy. 19. Common CSI examples. AWS EBS CSI. Provisioner, ebs.csi.aws.com. Parameters, type GP3, FS type, ext4, ext4. GCP persistent disk CSI. Provisioner, pd.csi.storage.gke.io. Parameters, type PD standard. Azure Disk CSI. Provisioner, disk.csi.azure.com. Parameters, SKU name, standard SSD LRS. NFS subdir external provisioner. Provisioner, katesigs.io. NFS subdir external provisioner. Parameters, path pattern. .pvc.namespace. .pvc.name. 20. Realistic exam task example. Task. Configure a storage class in PVC using the local path provisioner for a 2 GB volume. Mount it to a pod. Verify the pod can write data. Then delete all resources, ensuring the volume is cleaned up. Step 1. Create the storage class. Kind, storage class. Metadata, name, local SC. Provisioner, rancher.io, local path. Reclaim policy, delete. Volume binding mode, wait for first consumer. Step 2. Create the PVC. Kind, persistent volume claim. Spec, access modes, read-write once. Resources, requests, storage, 2 GB. Storage class name, local SC. Create a pod using it. Kind, pod. Spec, containers, volume mounts, name, vol, mount path, /data. volumes, name, vol, persistent volume claim, claim name, task, PVC. Step 4. Verify inside the pod. kubectl exec-it write test --cat /data/hello.txt. Output hello. Step 5. Delete PVC and pod, then check PV deletion. kubectl delete pod write test PVC task PVC. kubectl get PV. PV should be gone if reclaim policy equals delete. 21. Security considerations. 1. Namespaces and access. PVCs are namespace scoped. PVs are cluster scoped. Use RBAC and quotas to prevent abuse. 2. Reclaim policy. Avoid leaving sensitive data behind with retain unless intentional. 3. Encryption. Many CSI drivers, EBS, Azure, Ceph, support encryption at rest, configured through parameters or Cloud Console. 4. Snapshots and clones. Some drivers allow volume snapshot class and cloning. These extend storage classes for backup workflows. 22. Resource quotas and limits. Admins can control how much storage each namespace can consume. Example resource quota. Kind resource quota. Metadata name storage quota. Namespace dev. Spec hard. Request.storage 50 gigabytes. Persistent volume claims 10. If users exceed these, new PVCs will fail with error exceeded quota, storage quota. 23. Summary table. Concept, persistent volume, object, PV, scope, cluster, created by admin or provisioner. Key spec fields, capacity, access modes, reclaim policy. Concept, persistent volume claim, object, PVC, scope, namespace, created by user. Key spec fields, access modes, resources.request.storage. Concept, storage class, object, SC, scope, cluster, created by admin. Key spec fields, provisioner, parameters, reclaim policy. Concept, dynamic provisioning, object, not applicable, scope, automatic, created by storage class plus PVC. Key spec fields, enabled by storage class. 24. Best practices. Use wait for first consumer in multi-zone clusters. Use descriptive storage class names. Fast, standard, archive. Default reclaim policy equals delete unless retention is required. Enable allow volume expansion when supported. Test CSI driver health regularly. kubectl get CSI drivers. kubectl get CSI nodes. Keep one storage class per cluster. Keep one default storage class per cluster. 25. Key commands cheat sheet for CKA exam. List storage classes. kubectl get SC. Describe one. kubectl describe SC name. Create a PVC. kubectl apply -f pvc.yaml. Watch PVC bind. kubectl get PVC-w. View associated PV. kubectl get PV. Describe PV. kubectl describe PV name. Check CSI drivers. kubectl get CSI drivers. Patch reclaim policy. kubectl patch PV -p spec persistent volume reclaim policy delete. These are quick commands to recall during an exam scenario. 26. Cleanup tips. To ensure your environment resets cleanly, kubectl delete pod, SVC, PVC, PV, storage class, --all. Verify all PVs are gone. kubectl get PV. If a PV is stuck and released, you may need to manually remove claim ref before deletion. Conceptual analogy. Think of the workflow like cloud hotel automation. Storage class, hotel booking system, defines room type and automation. PVC, guest reservation, request a room. PV, physical room created on demand. Reclaim policy, clean room, delete, or hold for later, retain. CSI driver, hotel staff automating the process. This mental model helps explaining dynamic provisioning during interviews or oral exams. 28. Final recap. 1. Storage class defines how volumes are created. 2. PVC triggers when they are created. 3. PV represents the actual provisioning storage. 4. CSI drivers perform the backend creation. 5. Reclaim policy governs cleanup. 6. Volume binding mode manages scheduling correctness. 7. Allow volume expansion provides flexibility. 8. Default storage class automates selection. 9. Troubleshooting PVCs focuses on describe output and provisioner health. Dynamic volume provisioning makes Kubernetes storage as dynamic and self-service as its compute scheduling.